going to walk through a session applying the model to a particular input file that I set up. And first, I'd just like to mention some of the changes between the version that I'm working with now, version F versus E. The computation speed has been increased by about a factor of 4. I've added some more time series charts that compare the water quality and the hydrologic variables to get a sense of the dynamics of the SDA. I've added a button to run and save all cases in the project automatically. So in other words, once you've gone through the project and tested all your cases, you can run a batch process and it saves output in PDF and Excel forms. It also puts out approximate estimates of the areas exceeding 20, 15, and 10 parts per billion in each cell, and that's particularly useful for marsh simulations. I'm also using this nomenclature to help to make it easier to find a particular template or case that you want to try running. The demo file has 2 time series, one for SDA2 in compartment B, and the other time series for SDA 5.6, and that's been rescaled to provide the same average flow and load as SDA2. So the purpose of that is to show the effect of the basin flow dynamics on the simulated performance. I've also added a couple of cases with a B in front of it, and that means that I reduced the inflow concentration by 10%, and that can be easily adjusted to reflect effects of upstream control measures, or BMPs. And then the cell types are labeled with M for marsh, E for emergent, S for submerged cell, DR for a deep reservoir, and SR for a shallow reservoir. That's basically operated like an emergent STA. So we can put these different cell types in series within each case, and you can see over here the typical STA. If you're not concerned about simulating the marsh, you just want to meet the 13 parts per billion target, you could start with this ES case and adjust the cell areas and such. And then down here there's some sequences of shallow and deep reservoirs, and again with the BMPs upstream. And then there are 2 networks, one of which operates with SDA2 time series and the other with SDA 5.6. This gives you a sense of the flow dynamics for the 2 time series. You can see both of them are highly variable, where the shaded blue areas are the flow and the blue lines are concentration coming into the SDA, and the loads are even more spiky. But when you go to SDA 5.6, the spikiness is even larger, and there are long periods of no inflow, which causes the cells to dry out if you don't have storage. So we'll start off with this test case, which is just an emergent marsh with SDA2 time series. And here's the dynamic charts that I mentioned earlier, where I'm using these color codes to represent different variables. This is the inflow series, and this shows any bypass in flow and load, which in this case there wasn't any. And then the correlation, for example, between the SDA water depths and the inflow volume, and the predicted outflow and the inflow, outflow and depth, outflow and load, flow weighted mean concentration, and no, this is depth, and the line is flow weighted mean outflow concentration, flow and concentration, geometric mean, geometric concentration. We're using the flow-weighted values for design, but the geometric means are also calculated, and those are useful for interpreting the marsh simulations, because that's how the phosphorus criterion is measured. And then the correlation between the depth and the load and the storage in the cell in the biomass phosphorus relative to the inflow load. So you can see how that responds over a fairly long time frame. So if we go back here, I've set up another case that illustrates the sensitivity of simulation to the phosphorus calibration. So I've got one column for each of the SDAs, for each of the calibration parameters, and then I have another one that is separate, and this is sort of a research effort where I've actually calibrated to the performance of STA 3.4 and using a slightly different set of coefficients. So we can run that one. And down here at the bottom, it just shows you how far along it is in the calculations. The screen jumps around a little. But so if we look at the summary of the output graphs, this shows the effect of the calibrations where SAV gives the lowest outflow concentration, followed by the pre-existing wetland. The reservoir doesn't remove much phosphorus at all, and STA 3.4 is sort of intermediate because it's a hybrid calibration that reflects both emergent and SAV cells. All right. So, what do I want to show now? All right, well, let's look at a marsh simulation. So I'm running 5 cells in series here, and the reason for that is to get a graphic picture of the gradient moving downstream in the marsh, starting with basically an untreated discharge. Alright, so as I mentioned, this gives the, so that's the gradient, typical of what we measure in the marsh transect. And down here, over here on the side is the drop-down menu for variables. So if we want to plot the outflow concentration, and then you can see that it's, if you plot it on a log scale, it's pretty much log linear, which means it's an exponential decline. And that was basically the first STA design model, just used an exponential decay to represent the marsh. So let's go for, let's go this one. So this illustrates the typically if you're just designing an SDA, you would stop at the SAV cell, but here we're going to look at the downstream transect as well. So this one shows actually, because the SAV cell has already brought it down to something close to the target, there isn't much of a gradient left in the marsh. And okay, so that's what that shows. So you can see again the dynamics of the treated concentrations. That here. So there is generally a tendency in this simulation to have positive correlation between the concentration and the depth and with the inflow water load. So to show, whoops, that's not the one I want to see here. To show the, let's do a case where we don't meet the target with the SAV cell, and one simple way to do that is just to hit it with some more phosphorus. So if we go, let's say we increase the phosphorus load by, so this changes, this multiplies all the time series for flow and load by 1.25. So here the marsh is putting out slightly lower concentrations, and yeah, so it's putting out what, 19 versus, yeah. So if you wanted to, for example, look further down in the marsh, then we would just add more area. Let's say 100. Yeah, so you can see we've got much lower outflow concentration, so we can look at the dynamics of the marsh here. That's the outflow cell. Anyway, so this is what you might expect to see in a marsh that it's still got a little bit excess load in it, but it does. You can see that the concentrations are ranging from 5 up to 20 in a period of very high inflow. Geometric mean is the same pattern. So let's try, let's make one. Okay, let's put a DRES as a deep reservoir. Followed by an emergent. Okay, and I'm setting that the deep reservoir has a maximum depth of about 8 feet. And this one, the last time I ran it, I think it generated, there wasn't much bypass, but anyway, we'll run that one. So you can see the outlet hydraulics are different for a reservoir. So it operates, in this case, as a weir. So the reservoir is putting out higher concentrations, and the SAV is down to 10. And dynamics here, let's look at the reservoir dynamics. And you can see in this case there was a period of bypass in the simulation, and that was triggered when the water depths, it should have been triggered when the water depths were higher. Let's see, the bypass. Let's see where that. Anyway, we'll have to take a look at that one, because bypass is generated in March of 16. Well, I'll tweak that one. Let me go back and pull up another case. All right. Now, when we typically, if you put a reservoir upstream in an STA, you find the simulations that the benefits of the reservoir in terms of performance downstream is are best when you just specify a constant outflow for the reservoir. So it'll just follow that value. In this case, it's set at 500,000 cubic meters per year, and the input series has an array of up between 0.5 and 5 million cubic meters per day. But this one constrains it the most, and I think we'll see the reservoir behaves differently. So you can see that the outflow when the reservoir is constrained is capped here at 0.5. That's the constraint that we set in the input file. And this one did not generate any bypass. So if we look at the outflow concentration and other parameters, so you can see that the inflow concentrations for the well, let's go for the emergent. So immediately downstream of the reservoir, the inflow time series concentrations is not as variable, and it's even less variable for the inlet to the SAV cell. So the reservoir stabilizes both the flow and the inflow concentration. With the result, if we look at the summary, you can see we got very low. We got an SAV of 4.1. Now that's a little misleading because the reservoir is generating a lot of bypass that don't show up in the predicted marsh concentrations. Bypass load, so it's bypassing, what is it? 70% of the load with that constraint, so that's obviously unacceptable. So what we would do, we go back to the parameter sheet and we use, let's say, Q of, so that's it. Well, let's try 1. So it's 1 million cubic meter per day. So this will allow the reservoir to store more water, and it releases it at a higher rate so that it doesn't fill up as often and trigger a bypass. So the reservoir, you can see it's still capped. The inflows and the outflows are still capped, in this case at 1, but not as frequently. And the, whoops, not that one. The SAV cell still has a relatively stable inflow concentrations, and the performance is still good, but we're predicting an outflow concentration of 6 before we were getting, what, 4, but let's see how much. Yeah, we're still generating quite a bit of bypass. 50% is being bypassed, so if we want to get rid of that, we'd have to go to the tube cube, and that these selections can be easily modified by changing the input file. If you go through this exercise, it's not. You'll find that it helps. The reservoir helps, but it doesn't. It's not a real strong effect. But these simulations lean pretty heavily on the DMSTA phosphorus cycling algorithm. As I mentioned in the previous video, at smaller time steps, the model tends to underpredict the concentrations at high flows. So that's something we're working on. Okay, so okay, I already showed that. So let's try another one. Reservoir. I'm going to try a shallow reservoir. So the shallow reservoir, you can see the parameters are the same as the emergent marsh, and since I'm only specifying a 3.5 square kilometer in this case, it's not going to have much of an effect because that's small relative to what's already there. But if we change that to say, I don't know, 10. Let's see. But since this case already meets the Q-bell, if you add more upstream, I'm just gonna increase the load by 25%. I'm monkeying with these coefficients just to come up with a case that shows the sensitivity, and that's a real important part of the design process. I mean, the tendency historically, when this model's been used, people just look at that number and then they say, well, that's okay, we're done. But I really recommend looking at the graphs. There's 2 different ways to get a look at the time series. Either this, where you're just plotting one variable at a time, and this has more variables in it, and it shows correlations between the discharge and the water depth and the concentrations and the outflow volumes. And as I said, that's where the limitations of the model come in, because the model tends to overpredict for most time series the outflow concentrations when the flows are low, and underpredict them when they're high, but it all kind of cancel out when you calculate the flow weighted mean. And here, okay, so we're just about at the criteria, no, not quite, 16. So if we want it, let's say now we go back for this hypothetical case, we wanted to generate a 13 down here, we would just increase that by, well, let's go 5, let's go 15. typically run a reservoir, since they tend to be kind of boxy, you know, one tank in series, whereas a typical STA is operated, is simulated in with 3 tanks, which these tanks in series are just a way of modeling the hydraulics. They really don't have any particular design, they're not design parameters. So here, if we go back and look at the summary now, the SAV is still getting 60. Okay, well, let's whack it some more. Or treat it some more. And go to 25. No, go to 30. So we're kind of approaching a design that looks like STA 3.4 with a pretty big upstream shallow reservoir, compartment A. Yeah, so we got the goal there. It's about 13 or so, 14. So I think that demonstrates the sensitivity analysis concept. Let's try. What I want to do is compare the time series now. ES, that's the network. So okay, so now I'm going to demonstrate a case with a deep reservoir followed by an emergent SAV. Okay, so here's your reservoir, 3.5 square kilometers, 8 foot. So we're meeting 13 at the edge of the marsh. And how much are we bypassing with this case? So we're bypassing just a tiny amount. So that's probably an acceptable design. Now I want to illustrate what happens if we change the inflow time series. Yes, to STA 5.6. I think that was 3.5 on the other one. Yeah, see, with STA 5.6 now it's only meeting 24 instead of 13, so that just shows the effect of the flow dynamics, since the average loads are, and this one shows some bypass associated with these 2 large events. So, and that's when the reservoir fills up. So we're averaging the output here on a 30-day basis. I guess it would be interesting to show what the time series looked like if you select a shorter averaging period. So let's have a weekly output, 7-day averaging interval. So when you run at a shorter time step like that, it takes a tad bit longer, but the overall simulation times are not bad. Drink coffee or something. All right. Now you can see more of the shorter time frame. You can see, especially the bypass. Where's that? Bypass. Yeah, it doesn't show what the hell it's got. All right. This one, actually, with that case, it just about meets the. Yeah, it's bypassing 6.5% of the load, which is quite a bit. So that would be going to a downstream marsh. So that design probably wouldn't be acceptable. So you would have to jack up the reservoir size. Now let's try 10. Let's go to 12. So now that didn't really have too much of an effect. It's still eating 23 instead of 24, so I don't have in there that feature that I mentioned, constraining the outflows, which is typical design. Let's look at the dynamics of the flow. The reservoir. Okay, so let's constrain it at 1. Okay, so I'll go back. That's what I added. All right, run. Yeah, you can see that gave a much better performance, but it probably generated more, a lot of bypass. So you'd have to fiddle around with that to get to something that's, so that gets way too low. So we'll go back and change that to 20. Yeah, you can see with the inflow to the SAV cell is now capped. So we got a much stabler flow regime, but it's still, in the end here, it's still, basically it's drying out the SAV. So there would have to be some fiddling with the parameters of the reservoir simulation to try to keep the it could be that just as a consequence of the spikiness of the inflows, you can see there's very little inflow in this time series after 2017. So, but overall, that design gets us to 11. So iterations. Another thing that I wanted to mention on the emergent marsh, since we're the inflows to the marsh are now more stable, and the water depths are the marsh goes up to 80 at times. So that means that it's probably, you don't want to operate the marsh for 80 centimeters over an extended period. So to do that, we'd have to reduce the outflow from the reservoir. And yeah, so I think you get the gist of this. But one of the benefits, if you do get a case where, I think I showed one where the inflow concentrations and the water depths and the flows were fairly stable, there are benefits to that that are kind of intangible, that aren't reflected in the model, and that's basically if it's a healthier depth regime for the marsh, then the actual uptake rate of phosphorus may be better than what is in the initial calibration. So there's some, it builds in a certain amount of sort of a conservative estimate of the performance, and that's hopefully as we improve the model at a shorter time step, we'll be able to represent that. We do find that periods of dry out are beneficial to the marsh, and that's the way they're operated, taken offline every once in a while to allow maintenance, and that's part of the real-time operation that is, it's sort of built into this time series to begin with. So I want to demonstrate the network simulation, and here we have the same sequence of a deep reservoir followed by the emergent marsh and the marsh itself, and the NT cases are special for network simulations, and that's because if we just use the STA2 time series, well, if we just use the regular time series for either STA, there would be inflows from the watershed into this case, but the NT cases for the time series are set at zero flows because the downstream system gets outflow from the reservoir. So these simulations are linked. And down here it gives basically the numbers are used to identify where the outflow or the bypass of a particular case is going, and what we're mostly interested here is the marsh outflow. But again, this will give you an idea about how the marsh responds to what comes out of the STA. So we can run the model. Okay, so this gives you the what's coming out of each cell, in and out in terms of load and concentration. So in this case, the marsh, the downstream end, is at 6, and the STA is at 13, and there should be there's a little bypass associated with this case. And that the reservoir bypass, in this case, I'm sending it to the marsh. So this accounts for, so what we're seeing coming out of the marsh 6 accounts for all the flow and load. And one limitation when you run a network, only the last cell, the last case that you're running is currently loaded in a spreadsheet. So when you try to graph anything, we're only looking at marsh cells downstream. You can't get at the reservoir output. But if you want to look at the reservoir output, you can pause the simulation by, for example, one way, if you just delete that case for the downstream cell and reconfigure this, it'll stop. It'll just give you the reservoir output. Similarly, if you want to just look at the STA performance to take the marsh out. All right. And then I guess I'll show the same, let's see, DRES TS56. So these are the same parameters, but we're operating with the STA56 time series. Whoops. Intended to load the network and not the case, but and since you can see down here, I've selected save case output to a new Excel file. So for each of the 3 columns, there is a separate output file stored in a subdirectory, and then there's a sort of a printout of the entire spreadsheet, all the output screens. So you can use that for later reference. So I have to run this. So every time it loads a spreadsheet, it loads a case or a network, it blanks out all of the output rows. That's the first step. here we're generating, what, 10 parts per billion coming out. So before with the STA2 time series, what's coming out of the marsh is 10.6. No, with the STA2 we had 6 parts per billion, and now with the STA5 higher because of the increased flow dynamics. So that's about it in terms of the cases. Let me just show you. Let's see, network output time series, flow graph, or mass balance. Okay, so there's a sheet in here that has the actual network. So every time you run a network, this sheet at the end, it always generates a daily time series for each of the outlet streams that you specified. So yeah, I'm gonna get out of DMSTA. I want to show you some of the regional applications here. We don't need DMSTA. All right, so this is the input screen for restoration strategies, eastern and central basins, where after you run the network in DMSTA, you pull this up and you click here and it will load up the output from that run. And then, since that's already been done in this case, this screen lets you look at different parameters in the flow network, concentration, and so forth. And then just for reference purposes, there's a label. And these are how the accounting in this spreadsheet works in terms of showing the flows and loads. And the red cells here are inputs, and these are the parameters that were adjusted. Well, I created a set of values. The district did some tweaking and made slightly different assumptions, and they generated this sheet, and then a similar sheet for the western basin. Now I want to show the other one that I developed earlier that has, this one has all basins are run in one sheet, which is a little more convenient. Yeah, you can see all the basins are represented here, and it does some mass balance checks to make sure you got all these things hooked up. The inputs, it's the same general idea, but really the most difficult and laborious, well, it's the ROG flow spot series contents. Target flows, output cell data. Oh, okay. This is what I'm looking for. So this has a 45-year time series in it for all these terms that were extracted from the RSM, that's the district's daily hydrologic model. And then for each of those flow time series, there's a set of assumed concentrations for each of those basins, and those were all developed from historical data in their input on a separate sheet somewhere. I think it's here. Yeah, so this shows the monthly flow weighted mean concentrations assumed for each of the source terms. And to generate the inflow time series from this, it's just based on a seasonal distribution, which in some cases is not, there isn't much difference. So there's one, I think, a big limitation in this, and that is that it doesn't capture the correlations between flow and phosphorus load, or the tendency for the concentrations to be higher during periods of high flow within the same season. So that's an advantage of just running it on the historical time series. Captures that, and it may give a more accurate simulation. But the problem is that a lot of these scenarios that get run, the historical period doesn't entirely reflect the changes in the plumbing and operation. So it's more work to make those adjustments. So that's I think that's all I want to show for today. I will